Nobody warned you when you sat down today. That chair, the one that feels completely ordinary, is currently one of the most kinetically active objects in the known universe. You are spinning faster than the speed of sound. You are orbiting at 30 times bullet velocity. Your entire galaxy is being dragged sideways at 630 kilometers per second towards something so enormous we didn't notice it existed until the 1980s. 7 layers of motion stacked on top of each other, all invisible, all simultaneous, all real. Tonight we trace every single one, and at the very end we ask the question nobody can answer yet. If there is an 8th layer, something pulling our entire visible universe, where is it taking us? Settle in, subscribe. This one goes all the way to the edge. Part 1. The chair is not still. Here is something nobody told you when you sat down today. The chair underneath you, the floor beneath that, the building surrounding all of it, none of it is still, not even close. In fact, right now, without any sensation of movement whatsoever, your body is participating in 7 distinct and simultaneous motions, each one stacked on top of the last, each one more extreme than the one before it, and the combined speed of all of them together is so far beyond anything your nervous system was ever designed to register that your brain has simply filed the whole situation under not moving and moved on with its day. That is not a metaphor. That is a literal description of your current physical situation. And the strange thing, the thing that keeps pulling me back to this topic every time I think I've fully processed it, is not the speed itself. It's the fact that you cannot feel any of it. Not one layer. You are sitting in what might be the most kinetically active object in your immediate awareness. A chair that is hurtling through the cosmos at speeds that would vaporize any spacecraft we've ever built. And the experience of sitting in it is exactly as boring and uneventful as it has always been. You feel your own weight, maybe a little back discomfort, the temperature of the room, and that is it. The universe is moving around you and through you and with you at velocities that would be considered science fiction if they were attached to anything man-made, and you feel absolutely nothing. That is the thing this video is about, not just the speed, the invisibility of it. Because here is what I want to trace tonight, carefully and completely. I want to walk you through every measurable layer of motion that your body is currently embedded in. We are going to start at the floor and work our way outward. Earth's rotation, Earth's orbit, the sun's path around the Milky Way, the sun's drift through the local interstellar neighborhood, the Milky Way's slow fall toward its inevitable collision with Andromeda, the entire local group's motion towards something enormous that we only figured out existed in the 1980s, and then the expansion of space itself, which is a kind of motion so strange it barely deserves the same word. And when we have stacked all 7 of those layers on top of each other, I want to talk about the 8th one, the layer nobody can measure yet. The possibility, and it is a real possibility, being discussed by actual physicists and cosmologists right now, that our entire observable universe, everything we can see in every direction, the full 46 billion light-year sphere of existence that represents the totality of human knowledge about what is out there, may itself be moving relative to something we cannot detect, cannot reach, and may never be able to confirm. And I want to start by destroying a word. The word is stillness, because stillness, as it turns out, is not a state of the universe. It is a local illusion, a perceptual convenience, a story your brain tells itself so you can function without existential paralysis every time you try to sit quietly. Let's dismantle it. The chair you are sitting in right now is moving. We will get to exactly how fast in just a moment, but first I want you to notice something. The reason you do not feel it is not because the motion is small. The reason you do not feel it is because your body can only sense acceleration, changes in velocity, not velocity itself. This is one of the most important and counterintuitive facts in all of physics. And it has a name. It is called the equivalence principle. And Galileo was gesturing at it long before Einstein formalized it. If you are on a train moving at a perfectly constant speed on a perfectly smooth track, you cannot tell from inside the train whether you are moving or not. You can look out the window and check. You can feel the bumps and curves. But pure, smooth, constant velocity? Your nervous system has no receptor for it. It simply does not register. And this is why every layer of motion we are about to stack on top of you has remained invisible your entire life. Not because it isn't happening, because it is happening too smoothly for you to notice. Now, Earth's rotation. This is the first layer, and it is the one that surprises people the least on paper, but tends to hit them the hardest once they actually run the numbers. The Earth rotates once every 24 hours. That sounds almost boring when you say it that way, but let's translate it into something your body can work with. The Earth's circumference at the equator is approximately 40,000 kilometers. If you divide that distance by 24 hours, you get a rotational speed of roughly 1,670 kilometers per hour at the equator. 1,670. The speed of sound at sea level is approximately 1,235 kilometers per hour, which means that the ground beneath your feet, assuming you are anywhere near the equator, is currently moving faster than the sound of your own voice can travel through the air above it. Let me give you a second with that. You are sitting on a surface that is moving faster than sound, not in a rocket, not in a jet, in a chair, in a room, and you feel none of it. Now, that speed does decrease as you move toward the poles because you're covering a smaller circle in the same amount of time. At the latitude of London, it's around 900 kilometers per hour. At the poles, it drops to nearly zero. But the principle is the same everywhere. You are on a rotating sphere, and the rotation is fast enough that if the planet suddenly stopped, everything on its surface would be flung forward at whatever speed the surface was moving at that latitude. Buildings, oceans, everything. Like a car slamming into a wall. The Earth's gravity is strong enough that this doesn't happen when speeds fluctuate slightly. But as a thought experiment, it illustrates the raw scale of the energy we are all embedded in right now. And here is the historical piece that I think makes this even more interesting. For most of human history, the idea that the Earth was rotating was not just wrong, it was considered obviously wrong. Intuitively, viscerally, obviously wrong. Because here is the objection that smart, educated people raised for centuries. If the Earth is spinning that fast, why don't we feel it? Why don't objects fly off the surface? Why doesn't a bird that takes flight come down to a different spot? These were not stupid questions. They were reasonable extrapolations from everyday experience. If you spin a ball with mud on it, the mud flies off. If you're on a spinning carnival ride, you feel the rotation immediately. So the argument that Earth's rotation was undetectable seemed to many to prove that it wasn't happening. What those people were missing, and what took centuries to properly articulate, is that the human body does not detect velocity. It detects changes in velocity. If everything around you is rotating at the same rate, you do not feel the rotation. You feel nothing. The sensation only appears during changes, during acceleration, during braking, during the jerk of a turn. Smooth, constant rotation, invisible. And Earth's rotation is astonishingly smooth. So smooth that the best instruments we had for centuries couldn't detect it directly. The first truly convincing demonstration came in 1851 in Paris, when a physicist named Léon Foucault hung a 67-meter pendulum from the dome of the Pantheon. A pendulum, once set swinging, maintains its plane of motion relative to inertial space. It doesn't care about the Earth beneath it. It just swings. So if the Earth is rotating, the floor underneath the pendulum should rotate while the pendulum keeps swinging in the same direction. And that is exactly what happened. Over the course of hours, the pendulum's apparent direction of swing slowly rotated, tracing a circle across the floor. The floor was rotating beneath it. The earth was turning. You could watch it happen in real time, in a Paris cathedral, with a brass bob on a wire. There was no arguing with it anymore. Today we can do considerably better than Foucault's pendulum. Ring laser gyroscopes, instruments that use two beams of laser light traveling in opposite directions around a closed loop, can detect Earth's rotation with extraordinary precision. They are so sensitive that they can detect the tiny variations in Earth's rotation rate caused by weather patterns, the movement of tectonic plates, and even the slow transfer of angular momentum between the atmosphere and the solid Earth. Earth does not rotate at a perfectly constant rate. It wobbles, it slows, it occasionally speeds up slightly, and we can measure these changes to a precision of microseconds per day. There is one more thing about Earth's rotation that deserves a moment of attention before we move on, and that is how it has changed over time. Earth's rotation is not fixed, it is slowing down. The Moon's gravitational pull creates tidal bulges in Earth's oceans, and as Earth rotates under those bulges, the friction gradually drains energy from Earth's rotation and transfers it to the Moon's orbit, pushing the Moon slightly farther away from us over time. The current rate of slowdown is approximately 1.78 milliseconds per century. That sounds tiny, but extrapolate it backward and you reach a genuinely remarkable conclusion. When Earth was very young, roughly 4.5 billion years ago, a day on Earth lasted somewhere around 6 hours. 6 hours, 4 rotations per day. The sky cycled from day to night and back again while you were still in your first morning meeting. Life has evolved entirely within a gradually slowing rotation, and it continues to slow now while we sit here incrementally, imperceptibly, but measurably. That is layer 1, Earth's rotation, 1,670 kilometers per hour at the equator, slower at the poles, invisible to the body, measurable by lasers, and gradually decelerating toward a future so distant that you cannot meaningfully picture it. And here is what I want you to hold on to as we move to layer 2. This, the thing that took humanity centuries to accept, the motion so extreme it exceeds the speed of sound, the motion we can now measure to the microsecond. This is the smallest layer in the stack. This is the slowest thing your body is currently doing. What comes next is going to be an entirely different conversation. Part 2. The first crack Earth spins beneath you. So we have established the rotation. We have established that you are sitting on a surface, moving faster than sound, that your body cannot detect it, that it took humanity over 15 centuries after the Greeks first proposed a heliocentric model to actually prove that the ground beneath our feet was spinning. We have established that even this, the most intuitive and most argued about of our motions, the one closest to human scale, is completely invisible to the senses. And now I want to go a step further into the rotation itself before we exit it, because there is more here than just the speed number. The Coriolis effect. You have probably heard this term before. You may have heard the popular myth that it determines which direction water drains from a bathtub, which is not really true at household scales. At that size, the initial conditions of the water matter far more than the Coriolis force. But at the scale of weather systems, at the scale of ocean currents, at the scale of artillery shells travelling dozens of kilometres through the air, the Coriolis effect is not a minor correction. It is a fundamental shaper of the world you see every day. Here is what is happening. When you are standing on Earth and you throw an object, or when a parcel of air begins to move across the surface, you are both on a rotating platform, but different latitudes are moving at different speeds. The equator moves at 1,670 kilometers per hour. Somewhere closer to the poles, the surface is moving much more slowly. So, when air rushes from a high-pressure region toward a low-pressure region, it doesn't travel in a straight line relative to the ground. The ground underneath it is rotating, and the air carrying the rotational velocity of wherever it started, finds itself deflecting to the right in the northern hemisphere and to the left in the southern hemisphere. The result is that large weather systems, the cyclones, the hurricanes, the massive spiral structures you see in satellite images of Earth from space, are not spiraling because something is stirring them. They are spiraling because they exist on a rotating sphere, and the rotation curves their path into a spiral. This is Earth's spin, expressed in the shape of clouds. Every hurricane that has ever formed in the Atlantic, every typhoon in the Pacific, every massive low-pressure system that has ever dumped rain on a continent, all of them bear the fingerprint of the same rotation that is silently carrying you through space right now. Rotation has consequences. It writes itself into the world around us, and we just don't always recognize the handwriting. The same effect deflects artillery shells. During World War I, long-range guns, the kind firing shells, across distances of 30 or 40 kilometers, had to account for the Coriolis effect in their targeting calculations. At shorter ranges, it's negligible, but fire a shell at high velocity over a long enough distance, and the rotation of the Earth beneath it will push it off target by a meaningful amount. The men calculating those trajectories understood, at some level, that the ground was moving under the shell's flight path. That Earth's spin was a variable in an equation about where a piece of metal would land. And modern ring laser gyroscopes, the same instruments that now measure Earth's rotational speed with such extraordinary precision, are descendants of this same understanding. They are used in inertial navigation systems on aircraft, submarines, and spacecraft. They work by shooting two laser beams in opposite directions around a closed loop. If the system is rotating, the two beams travel slightly different distances and arrive slightly out of phase. That phase difference, measured with extreme accuracy, tells you exactly how fast and in what direction you are rotating, with no external reference needed. These gyroscopes can detect the rotation of Earth in real time. They are so sensitive that a person walking past the instrument in a lab has been known to introduce a measurable rotational signal through the gravitational perturbation of their body. These are not toys. These are the most sensitive rotation detectors ever built, and what they continuously confirm is that we are spinning, always, right now, measurably and precisely. But let's come back to the central question. Let's come back to stillness. Because the Foucault pendulum proved rotation to a 19th century audience, and the ring laser gyroscope proves it to a 21st century one, but in neither case does proof translate into sensation. The pendulum swings, the gyroscope measures, your body sits in the chair and reports nothing unusual, velocity without sensation, motion without experience. And this is the thing that matters most about layer 1. Before we move to layer 2, not any particular number, not any particular effect, but the principle that underlies all of it. Motion is real whether or not you feel it. Your experience of stillness is not evidence of actual stillness. It is evidence of smooth, shared velocity. And the reason this matters is that we are about to multiply the speed by a factor that makes Earth's rotation look like a slow walk. There is one more number I want to leave you with before we go. Earth's rotation is slowing. We established that 1.78 milliseconds per century. It is a crawling deceleration, imperceptible on any human timescale. But over the course of billions of years, it has already slowed from a 6-hour day to a 24-hour one, and it will continue. In the extraordinarily distant future, we are talking timescales that make the current age of the universe look like a coffee break. Earth's rotation may slow to the point where a day equals a month, the same face always pointing at the moon, tidally locked the way the moon is already locked to us. We would lose our weather patterns as we know them. We would lose our Coriolis-driven hurricanes. We would lose everything that comes from the spin. That is the future of layer 1. But right now, spinning at 1,670 kilometers per hour at the equator, faster than sound, invisible, measurable, real. It is the slowest thing on our list. Let's go to layer 2. Part 3. The bullet moment, Earth's orbit. The solar system has a shape. It is not a flat disk with a dot in the middle and a single circle around it, the way it looks in most textbook diagrams. It is a dynamic, three-dimensional system of objects constantly adjusting to each other's gravity, tracing ellipses that are never quite the same twice. But for our purposes, for understanding the velocity of Earth specifically, what matters most is this. Earth orbits the Sun at an average distance of approximately 150 million kilometers, completing one full orbit in 365.25 days, and doing so at an average velocity of approximately 29.78 kilometers per second. 29.78 kilometers per second. Let's slow that down into something you can hold. A rifle bullet leaves a standard military rifle at approximately 900 to 1,000 meters per second. Let's call it 1 kilometer per second for round numbers. Earth is moving at 29.78 kilometers per second. That is almost 30 times faster than a bullet. Your chair, the chair you are currently sitting in, the one that feels completely stationary, is moving through space at approximately 30 times the speed of a rifle bullet, and it has been doing this for 4.5 billion years, continuously, without ever slowing down, without ever stopping to refuel, without generating any sensation whatsoever in anything that has ever lived on its surface. There is an astronomical phenomenon that allowed us to actually measure this velocity, and it is one of my favorite examples of careful observation yielding a revolutionary conclusion. It is called stellar aberration, and it was discovered by an English astronomer named James Bradley in 1727. Here is what he noticed. When you observe a star through a telescope, the star does not appear exactly where you would expect it to be if Earth were stationary. It appears slightly shifted in the direction of Earth's motion. The amount of the shift corresponds exactly to the ratio of Earth's orbital velocity to the speed of light. Bradley noticed that the positions of stars shifted over the course of a year, cycling through a small ellipse as Earth moved around the Sun, and he correctly deduced that this was because Earth was in motion. The analogy that helps most people is rain. Imagine you are standing in perfectly vertical rain, falling straight down. If you are stationary, you hold your umbrella directly above your head. But if you start walking, the rain appears to come at you at an angle from slightly in front of you, and you have to tilt the umbrella forward to stay dry. You have not changed the rain. You have not changed the umbrella. You changed your velocity, and the apparent direction of the rain changed with it. Bradley's stellar aberration is exactly this. Earth is walking through the rain of starlight, and the stars appear shifted slightly in the direction we are walking. And the size of the shift told him precisely how fast Earth was moving. Now, I want to take a moment for the history here, because it matters. The idea that Earth moves around the Sun heliocentrism was proposed in ancient Greece. Aristarchus of Samos, around 240 BC, argued that the Sun was the center of the solar system and that Earth moved around it. For his trouble, he was more or less ignored for nearly 2,000 years. Ptolemy's geocentric model, Earth at the center, everything else going around it, dominated Western astronomy until the 16th century. It was not just cultural or religious conservatism that maintained geocentrism. The physics arguments against Earth's motion seemed genuinely compelling. If Earth moves, why don't we feel it? If Earth moves, why don't objects thrown into the air come back down in a different place? Why don't we see parallax shifts in the stars? These were real questions that geocentrists posed, and they didn't have bad answers. Copernicus published his heliocentric model in 1543, the year he died, having sat on the manuscript for years for reasons that seem to have been partly political and partly uncertainty. Galileo was put under house arrest by the Inquisition for supporting it. Kepler refined the orbits from circles into ellipses and introduced the laws of planetary motion between 1609 and 1619. Newton unified the whole thing under gravity in 1687, finally providing a mechanism, not just a description for why planets orbit the way they do. From Aristarchus to Newton, roughly 2,000 years for an idea that was correct the first time to finally be proven and accepted. And the payoff, the thing we eventually confirmed after all that time, is an orbit at 29.78 kilometers per second, 30 times the speed of a bullet. An orbit that traces an ellipse, meaning Earth is not always the same distance from the Sunday. At perihelion, which occurs around January 3rd each year, Earth is approximately 147 million kilometers from the Sun and moving slightly faster than average, closer to 30.3 kilometers per second. At aphelion, around July 4th, Earth is approximately 152 million kilometers from the Sun and moving slightly slower, closer to 29.3 kilometers per second. The difference is real and measurable, but small enough that we experience it as seasons, which are caused by axial tilt, not orbital distance, a fact that still surprises many people. Here is a way to feel the scale of this that I find genuinely affects people when they actually sit with it. At 29.78 kilometers per second, Earth covers its own diameter, 12,742 kilometers, in approximately 7 minutes. In the time it takes to make a cup of coffee from start to finish, Earth moves through a distance equal to its own width. While you were sleeping last night, Earth moved roughly 860,000 kilometers. That is more than twice the distance from Earth to the Moon, covered while you slept every single night. Every single night for 4.5 billion years. And here is what this layer does to the central thread of what we're building tonight. Layer 1, Earth's rotation was 1,670 kilometers per hour. Layer 2, Earth's orbit is 107,000 kilometers per hour. You just jumped by a factor of more than 60, and the sensory experience of both is identical. Absolute zero. Nothing. Complete stillness, reported faithfully by a nervous system that was never equipped to detect either of them. The deeper the motion, the more invisible it becomes. The faster the chair moves, the more still it feels. And we are not done adding layers. Because here is the thing. The Sun, the object Earth is orbiting, the object that all of this has been relative to so far, is not standing still. Part 4. The Sun is not standing still. Everything we have talked about so far has been motion relative to the Sunday Earth spins, Earth orbits. And those velocities are real and extreme and invisible. But we have been using the Sun as our reference point, and here is where it gets genuinely uncomfortable. The Sun is not a fixed point. The Sun is not sitting at the center of the solar system, waiting patiently for the planets to come around again. The Sun is moving. The entire solar system, every planet, every moon, every asteroid, every comet, the Voyager probes, the Parker Solar Probe is being dragged through space at a velocity that dwarfs everything on the list so far. The Sun orbits the center of the Milky Way galaxy. Specifically, it orbits the region around Sagittarius A star, the supermassive black hole that sits at the galactic center, roughly 26,000 light-years away from us. The Sun's orbital velocity around the galactic center is approximately 220 to 240 kilometers per second. Let's call it 230 for a reasonable middle estimate. 230 kilometers per second. We just went from Earth's orbital velocity of 29.78 kilometers per second to the Sun's galactic orbital velocity of 230 kilometers per second. We multiplied by nearly 8. And every layer before this, the rotation, the orbit, is still happening simultaneously, still stacked underneath this new velocity. Your chair is now carrying all three at once, and the third one alone is moving 8 times faster than the velocity that already felt incomprehensible. To make 230 kilometers per second concrete, the Parker Solar Probe, which became the fastest human-made object ever built when it achieved speeds of approximately 192 kilometers per second during its closest solar approaches in 2024, is slower than the speed at which your chair is being carried around the center of the Milky Way right now. The fastest thing humanity has ever launched into space, a machine we built specifically to go fast, shaped and tested and optimized to survive the sun's atmosphere, cannot keep pace with the ordinary motion of the solar system through the galaxy. We built the fastest thing humans have ever made, and it is still outpaced by the casual orbital velocity of a star that has never tried to go anywhere. The galactic year, the amount of time it takes the sun to complete one full orbit around the Milky Way, is approximately 225 to 250 million years. Let's call it 230 million, because we are comfortable with round numbers now. The sun has been around for about 4.5 billion years. That means it has completed approximately 19 to 20 orbits of the Milky Way since it was born. 19 or 20 galactic years. When the sun began its current orbit, its 20th lap, the one it is on right now, the most complex life on Earth was early dinosaurs. When the sun began its 19th lap, there were no dinosaurs. There were not yet mammals. We were somewhere in the Permian period, before the great extinction event that wiped out over 90% of species on Earth. One orbit of the galaxy ago, the Permian extinction was still in the future. 2 orbits ago, the first forests were appearing on land. 5 orbits ago, the first fish were experimenting with crawling out of the water. 20 orbits ago, nothing. The sun didn't exist yet. The solar system didn't exist. Whatever preceded it was still coalescing from the remnants of older stars. We are young. We are on only our 20th lap around a galaxy that has been spinning for over 13 billion years. Now, here is an additional layer within this layer that I don't want to skip. The sun does not orbit the Milky Way in a simple flat circle. It bobs. Like a dolphin moving through water, the sun oscillates above and below the galactic plane as it orbits. The galactic disk, the flat structure of the Milky Way that you see as the bright band of stars crossing the night sky, has a gravitational midplane. The sun is sometimes above it, sometimes below it, oscillating with a period of roughly 60 to 70 million years. Right now, astronomers believe the sun is slightly north of the galactic midplane and moving further in that direction before it eventually curves back. Why does this matter? Because some researchers have speculated, and I want to emphasize this is speculative, not confirmed, that this vertical oscillation through the galactic plane may be correlated with periods of increased comet bombardment or other disruptions to the solar system, which might in turn be correlated with mass extinction events on Earth. The timing is rough, and correlation is not causation, and the Milky Way's structure is messy enough that the hypothesis has serious complications. But the idea that the sun's bobbing path through the galaxy might have influenced the history of life on Earth by periodically dipping the solar system into regions of higher interstellar material density, that idea is not dismissed. It is actively argued about. It is an ongoing conversation in astrophysics, and it begins from the simple observation that the sun is not just orbiting the galaxy, but doing so in a graceful, slow, three-dimensional wave. And all of this, the galactic orbit, the vertical oscillation, the entire motion of the sun through the Milky Way, is layered on top of Earth's orbit, which is layered on top of Earth's rotation. Your chair is doing all three simultaneously. The third layer alone is 8 times faster than the second, and we are still not done, because while the sun is orbiting the galactic center, it is also moving relative to its immediate neighbors, the local stars, in a way that is distinct from its galactic orbit, and that distinction opens up an entirely new kind of motion to talk about. Part 5. The interstellar wind you cannot feel. There is a concept in astronomy called the local standard of rest. It is, roughly, the average velocity of the stars in the sun's immediate galactic neighborhood. the stars that are close enough to us that their motion through the galaxy is representative of our region. When you measure the sun's velocity relative to this local standard of rest, you get approximately 13.4 kilometers per second. This is the sun's peculiar velocity, its individual motion through the neighborhood, separate from and in addition to the overall galactic orbit. Think of it the way you might think of people on an escalator. The escalator represents the galactic orbit, carrying everyone in the same direction at roughly the same speed. But individual people on the escalator are also walking at their own pace, passing each other, drifting left or right, moving at slightly different rates. 13.4 kilometers per second is the sun's walking speed on the galactic escalator. But there is another layer here, something more specific and more physical, and this is where the interstellar medium comes in. Space between the stars is not empty. This is one of those facts that people intellectually accept, but rarely fully digest. The space between stars contains gas, dust, charged particles, magnetic fields, radiation, a thin but real medium that the sun and its solar system are currently moving through. And the specific cloud we are currently moving through has a name. It is called the local interstellar cloud, sometimes called the local fluff, and the sun is moving through it at approximately 22 to 26 kilometers per second. We have been inside this cloud for somewhere between 45,000 and 150,000 years, and we will exit it at some point in the next 10 to 20,000 years, at which point we will enter a different region of interstellar space called the G cloud. How do we know this? Several ways, but one of the most compelling is a NASA mission called IBEX, the Interstellar Boundary Explorer. IBEX detects neutral atoms that flow into the solar system from interstellar space. These atoms, primarily hydrogen, helium, oxygen, and neon, travel inward from outside the heliosphere, and by measuring their direction, speed, and composition, we can characterize the interstellar medium we are moving through. It is a bit like holding your hand out the window of a moving car to feel the wind, except the window is the boundary of the solar system, the car is the sun and all its planets, and the wind is made of interstellar gas. And then there is Voyager 1. Launched in 1977, Voyager 1 crossed the heliopause, the boundary where the sun's solar wind gives way to interstellar space in 2012, becoming the first human-made object to enter interstellar space. What it found was not nothing. It found a region of increased plasma density, increased magnetic field strength, and a definable boundary between the environment created by the sun's output and the general interstellar medium. The heliosphere, the sun's sphere of influence, the bubble of solar wind that surrounds the entire solar system, is not just an abstract concept. It is a real physical structure, and it is moving through the interstellar medium the way a ship moves through water, creating a bow shock in the direction of travel. This is the sun as a vehicle, not just orbiting, not just bobbing, but actively ploughing through material, surrounded by a magnetic bubble, leaving a tail behind it in the direction we came from, pressing forward into new interstellar territory every second. The entire solar system is a ship, and it has always been moving. And here is the thread that pulls this back to what we are building tonight. None of this, not the galactic orbit, not the interstellar drift, not the movement through the local interstellar cloud, generates any sensation on Earth. No wind, no resistance, no turbulence. We are embedded inside the heliosphere, inside the bubble, and the bubble itself is what is interacting with the interstellar medium. We are passengers inside a passenger inside a passenger, and every container around us is invisible and silent. The solar system may also be in the process of transitioning from the local interstellar cloud into the G cloud. If this transition happens, and current models suggest it could happen within the next few thousand years, the interstellar environment around us will change. The heliosphere may respond. The cosmic ray flux reaching Earth might shift. It is not a dramatic event in human terms. it would not cause an extinction or a crisis. But it is a genuine change in the environment through which we are sailing, and it is already in progress while we have this conversation. That is layer 5. But we are not talking about layers in isolation tonight. We are talking about a stack, a cumulative pile of simultaneous motions that your body is performing right now, without your awareness, without your consent, without generating the faintest sensation of movement. Earth's rotation at 1,670 kilometers per hour, Earth's orbital velocity at 107,000 kilometers per hour, the Sun's galactic orbit at approximately 828,000 kilometers per hour, the Sun's motion through the local interstellar cloud at an additional 80,000 to 93,000 kilometers per hour. These are not alternative velocities. These are cumulative. They all happen at once. And we have 2 more major layers to add before we even get to the largest measured motion, and after that we will talk about the one that may not be measurable at all. Part 6. The slow collision already happening. On a clear night in the Northern Hemisphere, if you know where to look, and it is genuinely easy once someone shows you, you can find the Andromeda Galaxy with your naked eye. It appears as a faint smudge of light, barely brighter than the background sky, in the constellation Andromeda, not far from the Great Square of Pegasus. It is not dramatic, it does not look like much, but that faint smudge is a collection of roughly 1 trillion stars, making it substantially larger than the Milky Way itself, and it is currently on a direct approach course toward us. Andromeda is approaching the Milky Way at approximately 110 kilometers per second. Astronomers have known it was approaching since 1912, when Vesto Slipher, working at the Lowell Observatory in Arizona, measured its spectrum and discovered that the light from Andromeda was blue-shifted. Redshift means something is moving away. Blue shift means something is moving toward you. The light from Andromeda is compressed, shortened, pushed toward the blue end of the spectrum because Andromeda is getting closer to us with every second that passes. The predicted collision, or more precisely, the predicted merger, is estimated to occur in approximately 4.5 billion years. These timescales are so large that the word predicted feels almost strange. It is less a prediction than a scheduled event, a date already set on the cosmic calendar. The gravitational dynamics of 2 galaxies approaching each other at this distance and velocity leave very little room for alternatives. Andromeda is coming. The Milky Way is not capable of getting out of the way. The merger will happen, but here is the misconception that almost everyone has about this event when they first hear about it. The merger of 2 galaxies does not look like a collision in the way we normally picture collisions. Stars are extraordinarily far apart from each other relative to their own size. The average distance between stars in our region of the Milky Way is roughly 4 to 5 light years. The diameter of a star like the Sun is about 1.5 million kilometers. If you scaled the Sun down to the size of a marble, about 1 centimeter, the nearest neighboring star would be approximately 300 kilometers away. That is how sparse the stellar distribution is. When 2 galaxies merge, the vast majority of stars in both galaxies will never come anywhere close to each other. The galaxies will pass through each other and interact gravitationally, but actual stellar collisions will be extraordinarily rare. What will happen is this. The gravitational interaction will disrupt the orbital structures of both galaxies. Stars will be flung into new orbits. Gas clouds in both galaxies will collide. Gas clouds do fill space much more densely than stars, and those collisions will trigger enormous waves of star formation, lighting up both galaxies with young, hot, bright stars. The combined object will oscillate and distort over hundreds of millions of years before eventually settling into a new, merged galaxy, a structure astronomers have taken to calling Milkomeda, a name that is equal parts functional and a little bit charming. Milkomeda will be an elliptical galaxy, probably, rather than the spiral structures both of its parents currently display. No more sweeping spiral arms. Just a diffuse, rounded cloud of stars, billions of them, orbiting a common center. Now, the merger itself is 4.5 billion years away, but the motion is happening right now. Andromeda is already closer to us than it was yesterday. This is not a future event in the sense of something that has not yet begun. It is an ongoing process that is currently underway, adding another layer to the stack of motions your body is already embedded in. The Milky Way and Andromeda are in a gravitational relationship that has already begun its slow, inevitable culmination. You are living in the early stages of a galactic merger event, and the fact that the event takes billions of years to complete does not change the fact that it is currently in progress. There is also a modern refinement to the story, courtesy of the Gaia Space Telescope. Early measurements of Andromeda's approach suggested a nearly head-on collision with minimal sideways motion. Gaia's precise measurements of Andromeda's proper motion, its actual movement across the sky, not just toward or away from us, have revealed that there is some sideways component to its velocity. This means the merger might be slightly less head-on than originally thought. Some models now suggest a more grazing encounter on the first pass, with a full merger taking longer and involving more complex dynamics. But the fundamental conclusion is unchanged. Andromeda is coming. It is approaching at 110 kilometers per second, and it has been approaching since before humans existed. One more thing before we move on, because it belongs here. The Milky Way itself is not stationary within its local neighborhood. The local group, the cluster of roughly 80 galaxies to which the Milky Way and Andromeda both belong, a cluster that spans roughly 10 million light-years, is itself moving. And understanding how it is moving, and toward what, takes us to the largest coherent motion that human science has ever managed to map. Part 7. Ambient Zone, looking at Andromeda. Let's slow down for just a moment. Just a moment before we go to the largest motions. Go outside on a clear night and find Andromeda, that faint smudge of light that you can just barely make out if you know where to look. The photons that hit your eyes when you look at it left their source approximately 2.5 million years ago. 2.5 million years. When that light began its journey toward you, Homo sapiens did not yet exist. Our ancestors were early Homo, possibly Homo habilis, making crude stone tools in East Africa. The anatomically modern human brain, the specific configuration of neurons and networks that is currently processing this sentence, was not yet present anywhere on Earth. And the light that those ancestors never saw, that no human being has ever seen until tonight, because it has been traveling for 2.5 million years, that light hits your eye when you glance at a smudge in the sky on a clear night. You are receiving a message from before your species, from before your language, from before fire was controlled or stones were shaped with intention. And here is the thing that ties this back to everything we are building. You are not looking at a stationary object. You are looking at the source of the light that left 2.5 million years ago, and that source has been moving toward you at 110 kilometers per second this entire time. In the 2.5 million years that light was traveling, Andromeda has covered an additional distance toward the Milky Way. You are moving toward it. It is moving toward you. The past is in your eyes, the present is in the math, and the future, the merger, is already being written in the gravitational equations that neither galaxy can rewrite. You are not an observer outside this process. You are inside it, moving, always moving. Part 8. The Direction of Everything, CMB Dipole. If you want to find the closest thing the universe offers to an absolute rest frame, a reference point against which all other motion could in principle be measured, you do not look at stars. You do not look at galaxies. You do not look at any of the familiar structures we have been discussing tonight. You look at the oldest light in existence. You look at something that has been traveling since before the Earth formed, before the Sun ignited, before the Milky Way had its current shape. You look at the cosmic microwave background, and what it tells us about our own motion is one of the most precise and quietly unsettling measurements in the history of science. Let's build this up properly, because it deserves the full treatment. The cosmic microwave background, the CMB, as it is almost universally abbreviated, is radiation that fills the entire universe, not just our region, not just our galaxy. Every cubic centimeter of space in the observable universe, and presumably well beyond it, is bathed in this radiation. It is left over from an era approximately 380,000 years after the Big Bang, when the universe had cooled enough for something remarkable to happen. Before that point, the universe was so hot and dense that electrons and protons could not combine any time they tried to form a hydrogen atom. A high-energy photon would immediately blast the atom apart. The universe was an opaque plasma, impenetrable to light. Photons could not travel freely. They were trapped, bouncing around in a fog of charged particles, unable to escape. And then, as the universe expanded and cooled below a critical temperature of approximately 3000 Kelvin, the electrons and protons finally combined into neutral hydrogen atoms. The fog cleared. The photons were released. They streamed outward in every direction and have been traveling freely ever since for approximately 13.8 billion years. We detect those photons today as microwave radiation, arriving from every direction in space. The expansion of the universe has stretched them enormously over 13.8 billion years, shifting them from the visible light they were when released all the way down into the microwave part of the spectrum, cooling them from 3000 Kelvin to approximately 2.725 Kelvin, just a few degrees above absolute zero. That is cold. That is extraordinarily cold. And the CMB arrives at that temperature with an uniformity that initially seemed almost suspicious to the astronomers who first mapped it carefully. Look in one direction, and it is 2.725 Kelvin. Look in a completely different direction, on the opposite side of the sky, and it is still 2.725 Kelvin. The CMB is the same temperature everywhere you look, to a precision of about 1 part in 100,000. For decades, this uniformity was slightly puzzling. If the early universe was really a chaotic, energetic explosion, why would the light left over from it be so extraordinarily uniform across the entire sky? Regions of the early universe that are now on opposite sides of the observable sky were so far apart in the early universe that, under standard physics, they should never have been in causal contact. They should never have had time to exchange energy and reach the same temperature. And yet, they have the same temperature. This is called the horizon problem, and it is one of the reasons cosmologists developed the theory of cosmic inflation, a period of extraordinarily rapid expansion in the universe's first fraction of a second that would have stretched a tiny, causally connected region into the entire observable universe, explaining the uniformity. But that is a conversation for another night. Tonight, what matters is the imperfection, because the CMB is not perfectly uniform. It is almost perfectly uniform, but almost is doing an enormous amount of work in that sentence. There are tiny fluctuations in temperature across the sky, and these fluctuations carry an extraordinary amount of information about the early universe, the distribution of matter, and the seeds of everything, every galaxy, every cluster, every filament of the cosmic web that subsequently grew from those initial density variations. Entire careers are built on analyzing CMB fluctuations. Satellites worth billions of dollars have been designed specifically to map them, and among all the fluctuations, there is one that is particularly relevant to what we are doing tonight, one that tells us not about the early universe, but about ourselves, about our own motion, about where we are going right now. When you map the CMB across the entire sky carefully, as the Planck Space Telescope did with extraordinary precision during its operational period between 2009 and 2013, you find a very specific, large-scale pattern. One half of the sky is very slightly warmer than the other half. Not dramatically, not in a way you could see with your eyes, or that would show up without careful calibration. The temperature difference is approximately 3.36 millikelvin, 0.003 of a degree. One side of the sky is 0.003 of a degree warmer than the other side. That is a number so small it seems like it should be meaningless, but it is not meaningless. It is one of the most important measurements in cosmology, because there is a very specific physical explanation for it, and that explanation tells us exactly how fast and in what direction we are moving. The explanation is the Doppler effect. You have encountered the Doppler effect every time an ambulance or a train has passed you. The siren sounds higher in pitch as the vehicle approaches. The sound waves are being compressed in front of the vehicle, increasing their frequency, and lower in pitch as it recedes, because the waves are being stretched behind it. The same physics applies to light. If you are moving toward a source of light, the light waves in front of you are compressed, shifted toward the blue end of the spectrum, and they carry slightly more energy than they would if you were stationary. If you are moving away from a source of light, the waves behind you are stretched, shifted toward the red end of the spectrum, carrying slightly less energy. More energy means higher temperature. Less energy means lower temperature. So when the CMB appears slightly warmer on one side of the sky and slightly cooler on the other, what that is telling you is that we are moving. The warmer side is the direction we are heading toward. The cooler side is the direction we are coming from. We are compressing the CMB photons in front of us and stretching the ones behind us, and Planck measured that asymmetry to a precision that, honestly, still impresses me every time I think about it. Measuring temperature differences of millionths of a degree across the entire sky, separating the CMB signal from every other source of microwave radiation between us and the edge of the observable universe, from our own galaxy, from other galaxies, from interstellar gas and dust, required instrument calibration and data analysis techniques that represent some of the finest precision science humans have ever done. And what that extraordinary precision produced is this number, 369.82 kilometers per second. That is our total velocity relative to the cosmic microwave background in the direction of the constellation Leo, 369.82 kilometers per second. This is not the velocity of the Earth relative to the Sunday. This is not the velocity of the Sun relative to the galactic center. This is the total, combined, cumulative velocity of everything Earth's spin, Earth's orbit, the Sun's galactic motion, our motion within the local group, our motion toward Andromeda, our motion toward the Great Attractor, all of it added together as a single vector, a single arrow pointing toward Leo, telling us that this is the net direction and speed of our travel relative to the oldest light in the universe. It is, as I said at the start, the closest thing physics currently offers to a measurement of absolute motion. Not because the CMB is metaphysically stationary, it is not, and we will come back to that, but because it represents such an ancient and uniform distribution of energy that measuring your velocity relative to it is as close as we can operationally get to measuring velocity relative to the universe itself. For practical purposes, for the purpose of answering the question, how fast are we really moving, and in what direction, the CMB dipole is the answer. 369.82 kilometers per second toward Leo. Now here is where the story stops being clean and starts being interesting. In recent years, astronomers have tried to verify this measurement using a completely independent method. The logic is straightforward. If the CMB correctly tells us that we are moving at 369 kilometers per second in a specific direction, then that motion should be detectable in other ways too. Specifically, it should show up in the distribution of distant galaxies across the sky. If you are moving through a universe that contains galaxies distributed roughly uniformly in all directions, you should see slightly more galaxies in the direction you are moving toward. You are approaching them, so you are collecting more of them in your forward hemisphere and slightly fewer in the direction you are moving away from. You should also see the galaxies in front of you appearing slightly brighter and slightly more numerous due to the same Doppler compression that warms the CMB in that direction. This expected pattern is called the radio dipole, the galaxy distribution equivalent of the CMB dipole, and it should match the CMB measurement in both direction and magnitude. When researchers measured the radio dipole using large catalogues of distant radio-emitting galaxies compiled from multiple sky surveys, the direction was indeed consistent with the CMB measurement, the same direction toward Leo as expected. But the magnitude was not consistent. The radio dipole was approximately 2 to 4 times larger than expected from the CMB velocity. There were significantly more radio sources in the direction of our motion than the CMB dipole alone would predict, not a little more. 2 to 4 times more, that is not a calibration rounding error. That is a genuine, significant, reproducible discrepancy across multiple independent datasets and multiple research teams who were not collaborating with each other. This is the radio dipole anomaly. It is unresolved. It is sitting in the published literature right now, actively being examined, re-examined, argued about, and modelled. Some researchers maintain that it is a measurement artifact, that the way radio galaxy catalogues are assembled introduces selection biases that mimic a larger dipole signal, that the catalogues are not as uniform across the sky as assumed, that different radio surveys have different sensitivities and coverages that could produce a spurious excess in one direction. These are legitimate technical concerns being seriously investigated. Other researchers argue that the signal is real, that it has appeared consistently across too many independent datasets to be easily dismissed as artifact, and that if it is real, it implies either that our motion through the universe is not fully characterized by the CMB dipole, or that the large-scale distribution of matter in the universe is more asymmetric than the standard model predicts. If it is real, and I want to be careful here, because this is genuinely not settled, the anomaly could be pointing at something in the structure of the universe that we do not yet understand. It could be evidence that the universe is not quite as uniform at the largest scales as the standard model assumes. It could be a hint that the CMB dipole is not telling the complete story of our motion. It is the kind of discrepancy that, if it holds up, will eventually require an explanation that goes beyond current models. And the fact that it connects directly to the question of how fast and in what direction we are moving makes it deeply relevant to everything we have been building tonight. One more clarification before we move forward, because it matters philosophically. The CMB dipole is described as the closest thing to an absolute reference frame, and I have been using language that implies measuring against the CMB is like measuring against the universe itself. But that is an operational convenience, not a deep truth. The CMB is not stationary in any absolute sense. It reflects the distribution of matter in the early universe, which itself was not at rest. It was the product of whatever initial conditions preceded the Big Bang, potentially including processes we cannot currently describe. Calling the CMB a rest frame is useful the same way calling sea level a reference for altitude is useful. It is a shared, consistent, measurable reference that allows meaningful comparisons. It is not the bedrock of reality. There is no bedrock of reality in this sense. There is no frame from which all other motion can be measured as absolute. Einstein showed us this, and the universe has not offered a counterexample since. What the CMB gives us is the best reference we have, the largest, oldest, most uniform distribution of energy we can access, and relative to it, we are moving at 369.82 kilometers per second toward Leo, and the layer that makes that number feel small is what comes next. Part 9. The Great Attractor and Laniakea. In the 1980s, a group of astronomers known informally as the Seven Samurai, a name they gave themselves with apparently no self-consciousness whatsoever, which I respect enormously, were trying to solve a problem that had been quietly irritating the cosmology community for years. Galaxies, in our local region of the universe, were not moving the way they were supposed to. The standard model of the time was clear enough in its predictions. Galaxies should be moving away from each other more or less uniformly, carried apart by the expansion of the universe, with small, local deviations caused by gravitational interactions with nearby clusters and groups. Tidy, predictable, the kind of behavior a well-behaved universe ought to produce. The data was not tidy, it was not predictable, and the universe, as it turns out, was not particularly interested in being well-behaved. What the Seven Samurai found, working through catalogues of galaxy velocities with the tools available in that era, was a large-scale, coherent flow, not random scatter, not small local deviations. A directed, organized motion of galaxies across a substantial region of space, all pulling in roughly the same direction, all moving as though being drawn towards something large, something massive, something that was generating a gravitational influence powerful enough to organize the motion of galaxy clusters across hundreds of millions of light years. And the maddening part, the part that made this discovery one of the stranger episodes in the history of modern astronomy, was that they could not see it. The source of this gravitational influence sat almost directly behind the plane of the Milky Way, hidden behind the dust and gas of our own galaxy's disk. The Milky Way was blocking the view of the thing that was pulling it. This region of obscuration has a name. Astronomers call it the zone of avoidance. It is the band of sky where the Milky Way's own material, the interstellar dust, the gas clouds, the sheer density of stars in the galactic plane, absorbs and scatters the light from objects beyond it, making extragalactic observation effectively impossible in visible light. The Great Attractor, as the Seven Samurai named their invisible gravitational giant, sat almost precisely within this zone. They could see its influence on the galaxies surrounding it on both sides, the way you can infer the shape of a boulder in a river by watching how the current distorts around it on both sides, even when the boulder itself is underwater and invisible. But seeing the source directly was not possible with the tools of the time. It took a different kind of light to see through the Milky Way's curtain. Radio waves and X-ray observations penetrate interstellar dust far more effectively than visible light, and as astronomers developed better radio and X-ray surveys of the sky, they were able to look through the zone of avoidance and begin identifying what lay behind it. What they found, centered on a region approximately 220 million light-years away in the direction of the Centaurus constellation, was a massive galaxy cluster designated Abell 3627, also known as the Norma cluster. It is a genuine heavyweight, a rich, dense concentration of galaxies, hot gas, and dark matter, the kind of structure that earns its gravitational reputation. But here is where the story expanded beyond what the Seven Samurai originally imagined. Subsequent observations and analysis revealed that the Norma cluster, massive as it is not the whole story. The Great Attractor is not a single object. It is a gravitational landmark within a far larger architecture, a region that contains multiple massive concentrations, flowing into each other, embedded within a superstructure so enormous that giving it a proper name took until 2014. That name is Laniakea, and it deserves a moment. The name was chosen by the team that formally defined the supercluster, led by astronomer Brent Tully of the University of Hawaii, working with data from a survey of galaxy velocities called the Cosmic Flows Project. Laniakea is a Hawaiian word meaning immeasurable heaven, and whoever made that naming decision understood the assignment. Laniakea is a supercluster, not just a cluster of galaxies, but a cluster of clusters, a collection of galaxy groups and clusters, all connected by the invisible threads of gravitational flow. It spans approximately 520 million light-years. Let that number sit for a second. 520 million light years. Light, traveling at 300,000 kilometers per second, the fastest anything in the universe can move, would take 520 million years to cross this structure from one side to the other. When that journey began, the most complex life on Earth was simple marine organisms. Multicellular life had barely gotten started. The entire history of complex animals, of plants colonizing land, of insects and reptiles and mammals and humans and everything we have ever done, all of that fits inside the time it would take a beam of light to cross the structure we call home. Laniakea contains approximately 100,000 galaxies. Its total mass is estimated at around 10 to the power of 17 solar masses, a 1 followed by 17 zeros, each zero representing another factor of 10 beyond the Sun's already incomprehensible mass. The Milky Way, with its 200 to 400 billion stars, is one of those 100,000 galaxies. Our local group, the 80 or so galaxies, including the Milky Way, Andromeda, and Triangulum, that form our immediate gravitational neighborhood, sits on the outer edge of Laniakea. We are not near the center. We are not in a privileged position within the structure. We are on the outskirts, the suburbs of a supercluster, and we are flowing inward. That word flowing is the key to how Tully's team actually defined and mapped Laniakea, and the method is worth understanding because it is genuinely elegant. They took velocity measurements for thousands of galaxies and separated each measurement into two components. The first component is the recession velocity, the speed at which the galaxy is moving away from us due to the expansion of the universe, which is predictable from the galaxy's distance and the Hubble constant. The second component is the peculiar velocity any additional motion the galaxy has on top of the universal expansion caused by local gravitational influences. The peculiar velocities are the interesting part. They tell you which direction gravity is pulling each galaxy, independent of the expansion. And when Tully's team mapped the peculiar velocities of thousands of galaxies across a large region of the sky, they saw something that looked unmistakably like a drainage pattern, like a watershed map where every stream and river and tributary traces back to the same basin. The peculiar velocities of galaxies across Laniakea all flow inward toward the region of the Great Attractor in coherent streams that converge on the same gravitational center. Laniakea is a cosmic watershed, and everything in it, including us, is water flowing toward the drain. The velocity of that flow, for our local group, is approximately 630 kilometers per second. 630. I want to stack this against everything we have covered tonight, because the comparison is genuinely striking. Earth's rotation at the equator is about 0.5 kilometers per second. Earth's orbital velocity is 29.78 kilometers per second, already 60 times faster than rotation. The Sun's galactic orbital velocity is approximately 230 kilometers per second, 8 times faster than Earth's orbit. Our total velocity, as measured against the cosmic microwave background, is 369 kilometers per second, incorporating all those previous layers. And now, the flow toward the Great Attractor and Laniakea's gravitational center, 630 kilometers per second, we have nearly doubled again. And none of it, not 1 kilometer per second of it, generates any sensation in your body whatsoever. This motion is not powered by anything. There is no engine. There is no propulsion. It is gravity, operating at the largest scales on which gravity has ever been observed to operate, curving space-time across hundreds of millions of light years and drawing everything in Laniakea toward its center in a slow, patient, irresistible flow that has been underway since long before the Earth existed and will continue long after it is gone. Now, there is one more piece to add here before we move forward, and it was proposed in 2017 by a team of researchers, including Yehuda Hoffman. The proposal is that our motion toward the Great Attractor is not only being driven by the attractor pulling us, it is also being driven by something pushing us from the other direction. In the region of the sky, directly opposite the Great Attractor, there is an enormous cosmic void, a region where matter is significantly less concentrated than the cosmic average. Voids do not attract. They are underdense, and the effect of an underdense region on surrounding matter is, in a gravitational sense, equivalent to a push matter flows away from voids toward denser regions, the same way air flows from high pressure to low pressure in the atmosphere. This void was named the dipole repeller, and Hoffman's team argued that it contributes roughly equally to our large-scale motion as the Great Attractor itself. We are not just being pulled toward one thing, we are being pushed from the other side simultaneously. A cosmic push-pull system operating across hundreds of millions of light years, moving your body at 630 kilometers per second through the universe right now, silently and completely without your knowledge, until approximately this moment in the video. This is the largest coherent motion that human science has successfully mapped. Beyond this boundary, the language of motion in the conventional sense begins to break down, because what comes next is not galaxies moving through space. It is not gravity curving paths across millions of light years. What comes next is something more fundamental and in some ways more strange than anything we have discussed so far. What comes next is the motion of space itself. Part 10. Space itself is moving. In 1929, Edwin Hubble published a paper that did something no scientific paper had done before, and very few have done since. It did not just add a fact to the existing picture of the universe. It dissolved the existing picture entirely and replaced it with something nobody had been psychologically prepared for. What Hubble showed, using observations of distant galaxies made at the Mount Wilson Observatory in California, was that those galaxies were moving away from us. Not some of them, not most of them, all of them, in every direction, at every distance. And not only that they were moving away faster the farther they were. A galaxy twice as far away was receding twice as fast. A galaxy 10 times as far away was receding 10 times as fast. The velocity of recession was precisely proportional to distance, in every direction, with no center, no edge, no preferred location. The relationship is now called the Hubble-Lemaitre law, the hyphenated name acknowledging that a Belgian Catholic priest and physicist named Georges Lemaitre had derived the same relationship theoretically in 1927, 2 years before Hubble's observational confirmation, and had not received the credit his priority deserved for several decades. Lemaitre was, by all accounts, a remarkable figure, a man who saw no contradiction between his faith and his physics, and whose physics was extraordinary. It was Lemaitre who first proposed what we now call the Big Bang, describing it as the universe expanding from a primeval atom. He was correct and underappreciated, and history has been slowly correcting both of those things. But the implication of the Hubble-Lemaitre law, the thing that makes it so conceptually disorienting even now, nearly a century after it was established, is not just that galaxies are moving, it is what kind of moving they are doing. Because here is the thing. If all galaxies in all directions are receding from us, the naive interpretation is that we are at the center of some enormous explosion, with everything flying outward from our location. But that interpretation has an immediate problem. It would mean we occupy a special, central position in the universe. And when astronomers looked at the data from any other galaxy's perspective, modeling what the expansion would look like if you were sitting in a different galaxy, anywhere else in the universe they found the same pattern. From anywhere in the universe, all other galaxies recede proportionally to distance. There is no center, there is no edge, there is no single point from which everything is flying outward. The correct interpretation, the one that Lemaitre and, independently, the Russian mathematician Alexander Friedmann had worked out from Einstein's equations of general relativity, is that space itself is expanding. The galaxies are not moving through space away from each other. Space is growing between them. The distances are increasing not because the galaxies are traveling, but because the medium they are embedded in is stretching. And this distinction, which might sound like philosophical hair-splitting, turns out to have enormous physical consequences. The raisin bread analogy is the one that tends to make this click for people, so let's use it properly. Imagine a loaf of bread dough with raisins embedded throughout it before baking. Now put it in the oven. As the dough rises, as it expands, every raisin moves away from every other raisin. A raisin that was 1 centimeter away is now 2 centimeters away. A raisin that was 5 centimeters away is now 10 centimeters away. The farther apart 2 raisins started, the faster they appear to be moving apart, because more dough is expanding between them. No raisin is at the center of this expansion. No raisin is moving through the dough. The dough itself is what is growing, and every raisin participates in the expansion equally, carried apart by the medium rather than propelling itself through it. Replace the dough with space and the raisins with galaxies, and you have a reasonable first approximation of what the expanding universe actually looks like. Now here is why this distinction matters so much that it is worth dwelling on for a moment. Einstein's special theory of relativity establishes, with extraordinary experimental support, that nothing can move through space faster than light. No particle, no signal, no information of any kind can traverse the distance between 2 points in space at a speed exceeding approximately 300,000 kilometers per second. This is not an engineering limitation. It is not something that better technology could overcome. It is a fundamental feature of the structure of spacetime, as deep and non-negotiable as any law physics has ever produced. But, and this is critical, this limit applies to motion through space. It does not apply to the expansion of space itself. Space is not a thing moving through space. It is the arena in which motion occurs, and the arena is allowed to grow, at any rate physics finds convenient, with no speed limit attached. The consequence of this is something that sounds, when you first hear it, like it must be wrong. There are galaxies in the observable universe that are currently receding from us faster than the speed of light. Not a few. In fact, the majority of the observable universe, everything beyond a distance of roughly 14 billion light-years, is currently receding from us at superluminal speeds. The space between us and those galaxies is expanding faster than light can cross it. And this does not violate relativity, because those galaxies are not moving through space faster than light. They are approximately stationary in their local regions of space. It is the space between us that is growing faster than light can traverse it. The raisins are sitting still. The dough is rising faster than light. This leads directly to one of the most conceptually striking features of the universe we live in, which is the cosmological event horizon. There is a distance currently estimated at approximately 16 billion light-years, beyond which, if we sent a light signal today, that signal would never arrive. Not because the destination is too far in an absolute sense, but because the expansion of space between us and the destination is fast enough that the signal would never gain ground. It would be like trying to walk toward a destination on a treadmill that is running backward faster than you can walk forward. You would never get there. The signal would travel forever and never close the gap. This means we are effectively isolated inside a bubble, not by walls, not by any physical barrier, by velocity. The universe beyond our event horizon continues to exist, continues to expand, continues to evolve. We simply cannot communicate with it, and it cannot communicate with us. And the bubble is shrinking over time, in the sense that more and more galaxies that we can currently observe are accelerating away from us and will eventually cross the horizon, becoming permanently unreachable. The night sky of the far future, if anything is around to observe, it will be darker and emptier than ours, because the galaxies that are currently visible will have receded beyond the horizon. The universe will become lonelier, one galaxy at a time, driven by an expansion that shows no sign of stopping. Which brings us to the discovery that genuinely shocked the physics community in 1998, and which earned its discoverers the Nobel Prize in Physics in 2011. Two independent research teams, one led by Saul Perlmutter, one led by Brian Schmidt and Adam Rees, were using a specific type of exploding star called a Type Ia supernova as a standard candle to measure cosmic distances. Type Ia supernovae are useful for this because they all explode with approximately the same intrinsic brightness, which means that by measuring how bright they appear from Earth, you can calculate how far away they are. The teams were using this technique to measure the expansion rate of the universe at different points in cosmic history, expecting to find that the expansion was slowing down. Gravity, after all, should be decelerating the expansion over time, all that matter pulling on all that other matter, gradually reining in the outward motion. What they found instead was that the expansion was speeding up, not slowing, accelerating. Galaxies farther away were receding faster than expected, not slower. The expansion of the universe was not being reined in by gravity. Something was overpowering gravity on the largest scales and driving the expansion to go faster and faster with time. That something was given the name dark energy, and it currently constitutes approximately 68% of the total energy content of the universe. Ordinary matter, the stuff you, the Earth, the stars, and every galaxy are made of accounts for only about 5%. Dark matter, the invisible gravitational scaffolding that holds galaxies together, accounts for roughly 27%. Dark energy, the thing accelerating the expansion of the universe, accounts for 68%. We are a 5% footnote in the energy budget of a universe dominated by things we cannot directly detect. We know dark energy exists because without it, the supernova observations make no sense. We know it constitutes 68% of the universe's energy because the numbers only balance when you include it at that proportion. But we do not know what it is. We have a mathematical placeholder for it, a term in Einstein's field equations called the cosmological constant, representing a constant energy density inherent to empty space, present everywhere uniformly, driving space apart at a steady rate. Einstein himself actually introduced this term and then removed it. When Hubble's observations showed the universe was expanding, he called it his greatest blunder. The irony is that the term he removed turns out to be necessary after all, just for a different reason than he originally included it. And now the mystery has deepened further. In 2025, the Dark Energy Spectroscopic Instrument DESI published results from the most comprehensive three-dimensional map of the universe's large-scale structure ever assembled, covering 11 billion years of cosmic history and tens of millions of galaxies. The data is extraordinary in its scope and precision. And what it suggests tentatively, with the caveats that preliminary results always carry, is that dark energy may not be constant. It may be evolving. The energy density of the vacuum, the thing driving the expansion, may have been weaker in the early universe and stronger more recently, or may be changing in some other pattern that the current data is only beginning to resolve. If dark energy is not a fixed cosmological constant, but a dynamic field that changes over time, the implications cascade in every direction. It would mean that the ultimate fate of the universe is not determined. The standard cosmological constant model points toward a future of endless, accelerating expansion, a cold, dark, increasingly empty universe expanding forever toward maximum entropy, what physicists call the heat death. But a dynamic dark energy could behave differently. It could weaken, it could reverse, it could strengthen dramatically, eventually overpowering not just gravity, but the electromagnetic and nuclear forces that hold atoms and nuclei together. tearing apart every structure in the universe down to the subatomic level in what is called the Big Rip. Or it could do something else entirely, something our current models do not yet describe, because our current models were built for a constant. We are in the position of having discovered that the engine driving the universe's largest scale behavior is not the simple, steady thing we assumed. It is something more complicated, possibly evolving, and not yet characterized. Every motion we have discussed tonight, the spin of the Earth, the orbit around the Sun, the galactic journey around Sagittarius A star, the flow toward the Great Attractor, the drift through the local interstellar cloud, the approach of Andromeda, all of it is motion within space, objects moving through a medium. This layer is different in kind, not just in scale. This is the motion of the medium itself. Space is not the passive backdrop against which the universe's drama plays out. It is an active participant, expanding, accelerating, carrying the galaxies embedded in it apart from each other at speeds that exceed the fastest thing physics allows to move through it. Your chair is not expanding with the universe because the gravity of the Milky Way holds the local group together against the expansion on local scales. But everything beyond the local group is being carried away, and the engine driving that process is 68% of everything, completely undetected except through its effects, and possibly changing. That is the seventh layer. It is the last one we can measure. And what it leaves us with, standing at the edge of what physics can currently reach, is a question rather than an answer. If space itself is expanding, if the very medium of existence is in motion, is there something outside it relative to which that motion could be described? Is there an eighth layer? And if there is, what would it even mean to measure it? That is where we are going next. Part 11. The crack in the model. There is a number that is currently keeping a significant portion of the cosmology community up at night. Not metaphorically. There are actual researchers at actual institutions who have spent years checking and rechecking their instruments, their data pipelines, their calibration procedures, their statistical methods, looking for the mistake that would make this number go away. And the mistake has not been found. The number remains, and the number should not exist. The number is 5.76. That is the current statistical significance, measured in standard deviations, of the disagreement between two independent measurements of the same thing. The thing being measured is the Hubble constant, the rate at which the universe is expanding, expressed as a velocity per unit distance, telling you how fast a galaxy is receding from us for every additional megaparsec of distance between us. It is one of the most fundamental numbers in cosmology. It describes the heartbeat of the universe, and we cannot agree on what it is. Here is the disagreement in full. There are two primary methods for measuring the Hubble constant, and they are genuinely independent. They use completely different physics, completely different instruments, completely different observational strategies, and completely different chains of reasoning. The first method works locally. You use the cosmic distance ladder, a sequence of overlapping distance measurement techniques that build on each other, starting with parallax measurements of nearby stars, moving to Cepheid variable stars, whose intrinsic brightness is predictable from their pulsation period, and extending to type Ia supernovae, which are bright enough to see across billions of light years, and which all explode with approximately the same intrinsic luminosity. By calibrating each rung of the ladder against the one below it, and then measuring the recession velocities of galaxies at known distances, you get a local measurement of the expansion rate. The value from this method, most recently refined by the SH0ES collaboration led by Adam Rees, is approximately 73 kilometers per second per megaparsec. The second method works from the opposite end of cosmic history. Instead of measuring how fast things are moving apart today, You look at the cosmic microwave background, the afterglow of the early universe, and use the standard cosmological model to predict what the expansion rate should be now, given what the universe looked like 380,000 years after the Big Bang. This method uses the acoustic oscillations imprinted in the CMB, the specific pattern of temperature fluctuations that encodes information about the early universe's density, composition, and geometry to constrain the cosmological model and derive the Hubble constant. The value from this method, from the Planck collaboration's analysis, is approximately 67.4 kilometers per second per megaparsec. 73 versus 67.4. The difference is approximately 8%. In everyday life, 8% sounds like a rounding error. In precision cosmology, 8% is an enormous gulf. These two measurements have been refined over years, with increasing data, increasing precision, and increasing care about systematic errors, and the gap has not closed. It has, if anything, slightly widened. The statistical significance of the disagreement is currently around 5 sigma 5 standard deviations, which is the threshold that particle physicists use to declare a discovery. A 5 sigma result means that if the two measurements were actually consistent and the discrepancy were just a statistical fluke, the probability of seeing a discrepancy this large by chance is roughly 1 in 3.5 million. This is not a fluke. Something is genuinely wrong. The question is what? The conservative explanations live inside the existing framework. Perhaps there are systematic errors in the distance ladder, subtle biases in how Cepheid variable stars are calibrated, or in how type Ia supernovae are standardized, that consistently push the local measurement too high. This possibility has been examined exhaustively. The James Webb Space Telescope has now independently confirmed the Cepheid measurements that underlie the local Hubble constant, reducing the likelihood that the local measurement is simply wrong. Perhaps there are systematic errors in the CMB analysis biases in how the Planck data was processed, or in how the acoustic oscillations were modeled. These possibilities have also been examined extensively by multiple independent groups using different analysis techniques. The systematic errors that would be needed to close the gap have not been found in either direction. The more radical explanations require modifying the standard cosmological model itself. The lambda cold dark matter model, named for the cosmological constant representing dark energy and the assumption that dark matter moves slowly, has been extraordinarily successful. It correctly predicts the large-scale structure of the universe, the pattern of CMB fluctuations, the abundances of light elements produced in the first few minutes after the Big Bang, and a vast range of other observations. It is one of the most successful physical models in history, and the Hubble tension is telling us it might be incomplete. Some researchers propose that there was an early dark energy phase, a brief period in the universe's history before the CMB was released, when dark energy was significantly stronger than it is today, speeding up the expansion at that epoch and shifting the predicted Hubble constant upward to match the local measurement. Others propose that dark matter is not perfectly cold, that it has some small but non-zero interaction rate or velocity dispersion that changes the acoustic oscillation pattern in the early universe. Others suggest that the universe is not as homogeneous at large scales as the standard model assumes, that we happen to live in a region of slightly lower than average density, which would make the local expansion rate appear faster than the global average. Each of these proposals preserves the general structure of the standard model while adjusting one component. None of them has yet produced a solution that fits all the data simultaneously without introducing new problems elsewhere. And then there is the anomaly we have already encountered once tonight, coming back around with renewed relevance. The radio dipole anomaly, the fact that the distribution of distant radio galaxies shows a dipole signal 2 to 4 times larger than the CMB dipole would predict. I mentioned it earlier and asked you to hold it in the back of your mind. Here is why it matters now. The Hubble tension and the radio dipole anomaly are independent measurements using independent data pointing in a similar direction. Something about our understanding of the universe's large-scale structure and evolution is not quite right. The model predicts one thing, the data shows another, and the discrepancies are large enough and robust enough across independent datasets and teams that dismissing both as measurement error is becoming increasingly difficult to justify. If the radio dipole anomaly is real, if there genuinely are 2 to 4 times more distant radio sources in the direction of our motion than there should be, the implications are significant. One interpretation is that the universe is not as isotropic as assumed, that matter is distributed differently in different directions at the largest scales, in a way that our standard model of a homogeneous, isotropic universe does not predict. Another interpretation connects directly to the possibility of motion beyond our current accounting, that we are moving faster or in a more complex way than the CMB dipole alone captures. And this second interpretation is the thread that leads us to dark flow. In 2008, a team of researchers led by Alexander Kashlinsky at NASA's Goddard Space Flight Center published a paper claiming to have detected something extraordinary. They had measured the velocities of hundreds of galaxy clusters using a technique called the kinematic Sunyaev-Zeldovich effect, which allows you to detect the motion of galaxy clusters through their imprint on CMB photons passing through the hot gas within the clusters, and found a large-scale coherent motion. Not the motion toward the Great Attractor, which was already known, a motion beyond that, a bulk flow of galaxy clusters extending across distances far larger than any known gravitational structure in the observable universe could explain. They called it dark flow, and the only explanation they could offer for a coherent motion at this scale, driven by no visible source within the observable universe, was gravitational attraction from something outside the observable universe, beyond the cosmological horizon, in the region of the cosmos that no signal from us has ever reached, and no signal from there will ever reach us. Think about what that means for a moment. We have established tonight that you are sitting in a chair, moving in 7 measurable layers of simultaneous motion. We have traced those layers from Earth's rotation all the way to the expansion of space itself. And now we are considering the possibility that the entire observable universe, the full 46 billion light-year sphere of everything we can see in every direction, is itself moving, being pulled or pushed or carried by the expansion of something larger in a preferred direction, a bulk flow with no visible source, a motion whose engine is on the other side of the horizon, permanently out of reach. Kashlinsky's team refined and extended their analysis in subsequent papers, maintaining that the signal was real and statistically significant. The response from the broader community was divided. The Planck collaboration, analyzing the CMB with the most precise full-sky map ever produced, looked for the dark flow signal and did not find it at statistically significant levels. Their analysis set upper limits on any bulk flow beyond the scale of the Great Attractor region that were consistent with the standard cosmological model's predictions. The case against dark flow is serious, and it comes from serious people using serious instruments. Kashlinsky and colleagues have continued to argue that the discrepancy between their result and Planck's non-detection comes from methodological differences, different cluster samples, different analysis techniques, different ways of extracting the kinematic Sunyaev-Zeldovich signal from the data, and that their signal is not ruled out by Planck's analysis. The debate is ongoing. It is not resolved. It sits in the literature, alive and contested, exactly where the most interesting science tends to live. What I find genuinely compelling about this entire collection of anomalies, the Hubble tension, the radio dipole anomaly, the dark flow claim, is not any individual result. It is the pattern. These are independent measurements, using independent methods, pointing toward a consistent possibility, that the universe as we have modeled it is missing something at the largest scales, that the motions we have mapped extraordinary as they are culminating in 630 kilometers per second toward the Great Attractor may themselves be embedded in a larger motion we cannot access, a flow beyond the flow, a current beneath the current we have already found. The philosophical weight of this possibility is worth sitting with. We have established tonight that your body is currently performing 7 simultaneous and cumulative motions, none of which you can feel, each one more extreme than the last. We have established that the largest of these measured motions is 630 kilometers per second toward a gravitational structure. We could not even see directly until we learned to look through our own galaxy with radio waves and X-rays. We have established that the expansion of space itself is accelerating, driven by a component that constitutes 68% of the universe's energy budget, and that we cannot directly characterize. And now we are considering whether all of that, the whole stack, from the spinning chair to the expanding cosmos, is itself embedded in a motion we cannot measure, driven by a source we cannot see, pulling our entire visible universe in a direction we can only infer from the faint statistical residues it leaves in our data. If dark flow is real, we are not just moving through the universe. We are being carried by something larger than the universe we can see. And we may never know what it is, not because we are not clever enough, not because our instruments are not precise enough, but because the source is on the other side of a boundary that physics itself has drawn the cosmological horizon, beyond which no signal travels and no observation reaches. We are inside a bubble, and something outside the bubble may be moving the bubble, and the bubble's walls are made of the speed of light and the expansion of space, and they will never come down. That is the crack in the model, a clean, sharp fracture running through several independent measurements, pointing toward the same unsettling conclusion. And it is the fracture that leads us, in the final part of tonight, back to where we started, back to the chair, back to the question of what stillness actually means when you peel back every layer of motion the universe contains and find that the peeling may never end. Part 12. The 8th layer, return to the chair. You are sitting in a chair. I want to start there, exactly where we started, because we have spent this entire video building something together, a stack, a cumulative architecture of motion, and before we go to the final question, the one that may not have an answer, I want to walk through every layer one more time, not as a summary, not as a recap, as a reckoning. Because I think if you actually feel the full weight of what your body is doing right now, simultaneously, in this moment, the 8th layer will land the way it deserves to. So, layer 1, Earth is rotating. At the equator, the surface beneath your feet is moving at approximately 1,670 kilometers per hour, faster than the speed of sound at sea level, faster than any conventional aircraft you have ever seen in the sky. The ground is moving faster than sound, and it has been doing so for 4.5 billion years, and your nervous system has never once registered it. Not a flicker, not a hint. Complete sensory silence in the presence of supersonic motion. The rotation is also slowing by 1.78 milliseconds per century, as the moon's gravity continuously drains angular momentum from Earth's spin and transfers it outward into the moon's orbit, pushing the moon a few centimeters farther away each year. 4.5 billion years ago, a day on Earth lasted 6 hours. The planet has been decelerating ever since, imperceptibly by any human measure, but relentlessly and measurably by physics. Right now, while you sit in that chair, the day is getting longer, by 1.78 milliseconds per century. You will not notice. Neither will anyone you know, or anyone they know, or anyone across a span of recorded history long enough to dwarf all of human civilization. But it is happening. Layer 1 is supersonic, invisible, and slowly dying, and it is the slowest thing on the list. Layer 2. Earth is orbiting the Sun at approximately 29.78 kilometers per second, 107,000 kilometers per hour, 30 times the speed of a rifle bullet leaving the barrel. At this velocity, you cover Earth's own diameter, 12,742 kilometers, in approximately 7 minutes. Think about what you were doing 7 minutes ago. Whatever it was, in that time, you traveled a distance equal to the width of the entire planet you are standing on. While you slept last night, you covered a distance more than twice the gap between Earth and the Moon. You do this every night for your entire life, every night for the entire existence of your species. The orbit traces an ellipse slightly faster in January when Earth is closest to the Sun, slightly slower in July when it is farthest, but always in motion, always at speeds that would be considered miraculous if attached to anything human-built. Layer 2 is 60 times faster than Layer 1, and equally, perfectly, completely invisible to every sense you possess. Layer 3. The Sun is orbiting the center of the Milky Way. The velocity is approximately 220 to 240 kilometers per second. Let's call it 230. That is roughly 8 times faster than Earth's orbit around the Sunday. It is faster than the Parker Solar Probe at its closest solar approach, the fastest object humanity has ever built, optimized specifically for speed, shaped like a racing machine designed to survive the Sun's corona. Your chair is moving faster than that right now, carried by the Sun's galactic orbit, and the Parker Solar Probe cannot keep up. The Sun has completed approximately 19 to 20 of these galactic orbits since it formed. One orbit takes approximately 230 million years, a galactic year. When the current orbit began, the earliest dinosaurs were just appearing on Earth. Mammals did not yet exist. Flowers did not yet exist. The continents were arranged completely differently. Our entire civilizational history, every empire, every war, every book ever written, every city ever built, every human being who has ever lived occupies a sliver of time so small relative to a single galactic orbit that representing it accurately on a timeline would require a line thinner than an atom. Layer 3 is 8 times faster than Layer 2, and we are still not close to the top. Layer 4. The Sun is also moving through the local interstellar medium at approximately 22 to 26 kilometers per second, relative to the gas cloud surrounding us. This motion is distinct from the galactic orbit. It is the Sun's individual drift through its local stellar neighborhood, through the specific cloud of interstellar gas called the local interstellar cloud that the solar system has been embedded in for somewhere between 45,000 and 150,000 years. The heliosphere, the vast magnetic bubble generated by the Sun's solar wind, the bubble that surrounds and shelters the entire solar system, is ploughing through this medium, creating a bow shock in the direction of travel, compressed on the forward side and stretched into a long tail behind us. We know this from the Voyager probes, which crossed the heliopause in 2004 and 2012 respectively, and from the IBEX satellite, which detected the inflowing stream of interstellar neutral atoms entering the solar system from outside. We are transitioning. In the next few thousand years, a blink by cosmic standards, the solar system will exit the local interstellar cloud and enter the neighboring G cloud, and the interstellar environment surrounding us will change. Layer 4 is a motion so subtle in the grand scheme that no spacecraft mission has ever been designed around it, and yet it is real, measured, and currently reshaping the boundary of the bubble we all live inside. Layer 5. The Milky Way is approaching Andromeda. The closing velocity is approximately 110 kilometers per second. The merger, the full gravitational coalescence of two galaxies, each containing hundreds of billions of stars, into a single merged system, is predicted to begin in approximately 4.5 billion years. But the motion is happening now. Andromeda is closer today than it was yesterday. The photons hitting your eyes when you look at that faint smudge in the night sky left their source 2.5 million years ago, when the ancestors of modern humans were using crude stone tools in East Africa and the anatomically modern brain had not yet evolved. In the 2.5 million years that light was traveling toward you, Andromeda has been closing the distance. You have been closing the distance. Two galaxies, each moving, falling toward each other under the mutual attraction of their combined mass, in a process that began long before humans existed and will conclude long after the sun has exhausted its fuel. Layer 5 is a collision in slow motion, already underway, absolutely certain, and currently invisible, except as a faint smudge that most people have never noticed in the night sky. Layer 6. The local group, the collection of roughly 80 galaxies anchored by the Milky Way and Andromeda, spread across a volume approximately 10 million light-years across, is flowing toward the Great Attractor region, toward the gravitational center of the Laniakea supercluster, at approximately 630 kilometers per second. 630. This is the largest coherent gravitational flow that human science has ever mapped. It is driven by the combined gravitational influence of the Norma cluster, the broader concentration of mass in the Great Attractor region, and the structures beyond it, including the Shapley supercluster, one of the most massive concentrations of matter in the observable universe. It is assisted from the opposite direction by the dipole repeller, the enormous cosmic void that pushes matter away from its underdense region toward the denser structures ahead of us. Push from behind, pull from ahead, 630 kilometers per second, your body embedded in it right now, and your body reporting nothing. Absolute stillness. The most sensitive motion detection system in the known world, the human vestibular apparatus, has absolutely nothing to say about 630 kilometers per second of coherent cosmic flow. Layer 6 is the largest motion we can measure, and it is not the last layer. Layer 7. Space itself is expanding, not galaxies moving through space, space growing. The medium of existence stretching, carrying everything embedded in it, apart from everything else, driven by dark energy, a component constituting approximately 68% of the total energy content of the universe, undetectable directly, characterized only mathematically, and recently suggested by the Dark Energy Spectroscopic Instruments 2025 results to be possibly evolving rather than constant. Your chair is not being carried apart from the Milky Way by this expansion, because local gravity holds the local group together against the expansion on these scales. But everything beyond the local group is being carried away, and at distances beyond roughly 14 billion light-years, it is being carried away faster than light can cross the gap. The universe is becoming less reachable every second. The cosmological horizon is tightening. Galaxies that are visible tonight will eventually redshift beyond detection, carried over the horizon by an expansion that nothing in physics limits. This is Layer 7. It is so different in kind from Layers 1 through 6 that it barely deserves the same word motion. But it is the most consequential motion of all, because it determines the ultimate structure and fate of everything, and it is driven by something we cannot explain. 7 layers, 7 simultaneous, independent, non-cancelling, cumulative motions, all happening to your body right now, all generating zero sensation. The stack is real. The stack is measured. The stack is you, right now, in the chair. And now the 8th. The 8th layer is not a measurement. I want to be precise about this, because precision matters when we are at the edge of what science can currently establish. The 8th layer is a possibility, an implication drawn from several independent threads of anomalous data that each, on their own, might be explainable as measurement error or model imperfection, but which together point in a direction that is difficult to ignore. Let me lay out those threads one final time, and then I want to tell you what they might mean. The Hubble tension. The universe's expansion rate, measured locally using the cosmic distance ladder Cepheid variable stars, type Ia supernovae, calibrated distance measurements built up rung by rung, gives a value of approximately 73 kilometers per second per megaparsec. The same expansion rate, predicted from the cosmic microwave background using the standard cosmological model, gives 67.4. The discrepancy is 5.76 standard deviations. Every reasonable source of systematic error has been investigated. The James Webb Space Telescope has independently confirmed the Cepheid measurements underpinning the local value. The gap has not closed. Something in the model is wrong, or something in the physics is missing. In the history of science, discrepancies of this magnitude and persistence have consistently preceded the discovery of something new: the orbit of Mercury and general relativity, the missing energy in radioactive decay and the neutrino, the rotation curves of galaxies and dark matter, the accelerating expansion of the universe and dark energy. The Hubble tension is the next entry in that list of uncomfortable numbers that refuse to go away until physics caught up with them. The radio dipole anomaly. The distribution of distant radio galaxies across the sky shows a dipole signal, more sources in one direction, fewer in the opposite direction, that is consistent in direction with our CMB measured motion, but 2 to 4 times larger in magnitude. Multiple independent teams using multiple independent galaxy catalogues have found this result. The most straightforward interpretation of a dipole in the galaxy distribution is motion we are moving toward the direction with more galaxies. But if our motion fully explains the CMB dipole at 369 kilometers per second, it should not produce a radio dipole 2 to 4 times larger. Either the catalogues are systematically biased in ways that have not been identified after extensive searching, or the universe is structured differently at large scales than the standard model assumes, or our motion is not fully described by what we have already measured: dark flow. The claim, made by Alexander Kashlinsky and colleagues at NASA and maintained through subsequent analyses, that galaxy clusters show a coherent bulk motion extending beyond the scale of the Great Attractor, beyond the scale of Laniakea, beyond any gravitational structure visible within the observable universe. A flow with no visible source. The Planck collaboration analyzed the CMB for this signal and did not find it at significant levels. Kashlinsky's team maintains the discrepancy is methodological, not physical, and that their signal survives scrutiny. The debate is unresolved. The possibility is not ruled out. And if it is real, there is only one class of explanation physics can currently offer: gravitational attraction from beyond the cosmological horizon, from structures we cannot see, from a region of the cosmos where our light has never traveled and never will. Now, here is the thing I want you to sit with as we reach the end of this. If the 8th layer exists, if all 7 of the measured motions we have traced tonight are themselves embedded in a larger motion, a bulk flow of the entire observable universe relative to something beyond its own edge, we may never be able to confirm it. And I do not mean never as in not in our lifetimes, or not with current technology. I mean never as in the physics itself may forbid it permanently. The cosmological horizon is not an engineering problem. It is a consequence of the finite speed of light combined with the accelerating expansion of space. Beyond a certain distance, the expansion is fast enough that no signal originating there can ever reach us, regardless of how long we wait, regardless of how powerful our instruments become, regardless of how clever our methods are. The information simply cannot cross the distance. If the source of a putative 8th layer motion lies beyond that horizon, we can only ever see its effects in the residues of anomalous data, in the tensions between measurements, in the cracks, in a model that fits almost everything but not quite everything, and never its source. We are passengers in a vehicle with no windows. We can feel the turns. We can measure the acceleration. We can map every road we have passed through, every gradient of the terrain beneath us, every layer of motion the vehicle is performing. But the hand on the wheel, if there is a hand, is outside the vehicle, and the vehicle has no windows, and the doors are sealed by the laws of physics themselves, and they will not open. This is not a failure of science. It is science doing exactly what science does, tracing the observable world to its edges, and then standing at those edges and being honest about what lies beyond them. The honest answer, at the edge of everything we can measure, is this: we do not know. We have 7 layers confirmed. We have anomalies suggesting an 8th. We have a horizon that may permanently conceal the source. And we have a model of the universe that is extraordinary in its successes and increasingly pressured at its seams. Let me bring it all the way home now. You are sitting in a chair. The chair feels completely still. Every proprioceptive signal your body generates, every output from your vestibular system, every reading from the gravity sensors in your inner ear, all of them agree. Nothing is happening. You are at rest. Every single one of them is wrong. You are spinning faster than sound. You are orbiting 30 times faster than a bullet. Your star is outpacing the fastest machine humanity has ever built on its journey around a galaxy so large that one lap takes 230 million years. Your solar system is drifting through a cloud of interstellar gas on its way to a different cloud. Your galaxy is falling toward another galaxy in a merger that will reshape both of them beyond recognition. Your supercluster is flowing at 630 kilometers per second toward a gravitational center that we could not even see until we learned to look through our own galaxy with radio waves. And the space you are embedded in is expanding, driven by something that constitutes 68% of the universe and that we cannot directly detect, at a rate that disagrees with our own theoretical predictions by nearly 6 standard deviations. And possibly all of that is itself in motion, relative to something beyond the edge of everything we can see, something whose gravitational signature may be whispering to us through the anomalies in our data right now, in the radio dipole and the Hubble tension and the contested signal of dark flow, something we may recognize as real long before we can ever confirm its source. A hand we can feel but cannot find. There is no still. There has never been a still. Stillness is the story your nervous system tells you because it has no reference point outside the motion you are embedded in. You are not a stationary observer watching the universe move around you. You are part of the motion. You are one of its expressions. The universe is not happening around you. The universe is happening as you, this particular arrangement of atoms, performing this particular set of simultaneous velocities in this particular chair, at this particular moment, in the 14 billion year story of everything. The chair you are sitting in is one of the busiest objects in the universe. It always has been, and now you know it.